Hello everyone, welcome to our presentation. In this presentation, we will discuss about how Office Multi-Light works using rules of inference. Before we go any further, let's first learn about the fundamentals of logic.
Okay, let's see our introduction. Our group is focusing on logic in designing efficient electrical circuit. Logic is all around us. Even in everyday system like office lighting is also a logic. Today we will explore how a simple office lighting system demonstrates fundamental concept of logic by examining how motion detectors, manual switches, and timers work together. You can understand how basic statement, logical connective, and rule of inference operate in real-world application. This practical example show us that logic is not just abstract theory. It is a powerful tool that helps us understand and design automated system. Okay, before we start with our project, I will explain for you basics that related to fundamental of logic. First of all is a statement and logical connective. Okay, first of all, we focus on a statement. What is a statement? A statement or a proposition is a declarative sentence that is either true or false, but not both. A simple statement is known as a primary statement. It can be represented by a variable x, v, p, q, and others. The variables that represent the statements are called propositional variables. The true value of a statement is true T if it's a true proposition and false F if it's a false proposition. The following are examples of a statement. Okay, let's see the example of a statement. So, first one, P. Phuket is the capital of Thailand. So, this is a statement, but it's a false statement. Next one is Q. 12 is an even number. So, this is a statement and this is a true statement. R. 4 plus 5 equal to 8. This is statement but is false statement. Lastly, S. A is a vowel. This is a statement and this is true. A. Put the book on the table. So, this is a not statement. B. Do you speak English? Also, not a statement. And lastly, sit down. This one also is a not statement. Next, we go through to logical connective. A logical connective is a symbol or word that conveys a specific logical operation, detecting how to process a statement or combination of statements. Logical operator can also be used to join or combine two or more statements to form a new statement. Okay, this is a logical connective symbol and represent. So the first one, negation. Negation is for not, conjunction for and, disjunction or conditional or implication if, then, and lastly biconditional if and only if. Okay, let's see the logical connective example. Let P, Sharifah is smart, and Q, Sharifah is honest. Construct the proposition symbol to represent the following statement. A. Sharifah is not smart but honest. B. Either Sharifah is smart or she is not smart but honest. C. If Sharifah is smart, then she is not honest. So, the answer for A, not P and Q. For B, P or not P and Q. And lastly, the answer is P implies to not Q.
Okay, next, what is an argument? Argument is a set of two or more sentences or beliefs. It is a collection of statements or prepositions, some of which are intended or provide the support or evidence for others. One of the sentence or beliefs is the conclusion. The rest are premises. If you can see right here, this is an example of arguments. If Ryan plays football, then he is healthy. If Ryan is not healthy, then he eats vegetables. Ryan plays football, or he does not even eat vegetables. Therefore, Ryan is healthy. You can make it as premises. First premises is P. P is, we can make it as Ryan plays football, and Q, Ryan is healthy, and R, Ryan eat vegetables. If you can see, the last of the sentence is Ryan is healthy. Ryan is healthy, we can make it as a conclusion.
Next, I will explain about the subtopic 5.8, rules of inference. Rules of inference are the templates for constructing valid arguments. They are the basic tools for establishing the truth of statements. Okay, right now is the list of rules of inference. Number one is modus ponens. The rules of inference is P. P implies Q, so the conclusion is Q. Number two, modus tollens. P implies Q, not Q, then the conclusion is not P. Number three, hypothetical syllogism. P implies Q, Q implies R, so the conclusion is P implies R. Number four, disjunctive syllogism. Rules of inference, P or Q, not P, then the conclusion is Q. Number five, addition. Rules of inference, P, so the conclusion is P or Q. Number six, simplification. Rules of inference, P and Q, the conclusion is P. Number seven, absorption laws. Rules of inference, P, Q, and then the conclusion is P and Q. Number eight, contradiction. Rules of inference, not P implies C, so the conclusion is P. Number 9. Conditional proof. Rules of inference, P and Q. P implies Q implies R, so the conclusion is R. Number 10. Proof by cases. Rules of inference, P implies R, Q implies R, then the conclusion is P or Q implies to R. Number 11. This constructive dilemma. Rules of inference, P implies Q, R implies S, P or R, so the conclusion is Q or S. Number 12. Destructive dilemma. Rules of inference, P implies Q, R implies S, not Q or not S, so the conclusion is not P or not R. So this is the example question for rules of inference. The question is, if Ryan plays football, then he is healthy. If Ryan is not healthy, then he eats vegetables. Ryan plays football, or he does not even eat vegetables. Therefore, Ryan is healthy. The P is Ryan plays football. Q, Ryan is healthy. Then R, Ryan eat vegetables. So, if Ryan plays football, then he is healthy. P implies Q. If Ryan is not healthy, then he eats vegetables. Is not Q implies R. Ryan plays football, or he does not even eat vegetables. Is P or not R. Therefore, Ryan is healthy. So the conclusion is Q. So the solution is we need to list the three premises first, which is P implies Q, not Q implies R, P or not R. So the next step is we take number 2 to do inverse. So the result is Q implies to not R. Next, we take number 1 and 4. we do proof by cases. So the result is P or not R. Last, we take number 3 and 5. We do modus ponens. So the result is Q. So that is the conclusion for this question.
Okay, this is our case study. First of all, scenario. It is 8 p.m. and the office light system is controlled by a motion detector, manual switch, and timer. The cleaning staff is scheduled to clean the office at night after working hours. The office light should be automatically turned on at 8 p.m. to ensure the cleaning staff can work in well-lit environment. However, no one is present in the office to activate the motion detector or the manual switch. The system relies on the timer to activate the light. The timer is set to turn the light on at 8 p.m. And since it's already that time, the light will automatically turn on as a plan. This is our study case that we can use in our scenario. If it is 8 p.m., the cleaner is at work. If the cleaner is not at work, then the light is turned off. It is 8 p.m. or the light is not turned off, therefore the cleaner is at work. If it is 8 p.m., then the cleaner is at work. If the cleaner is not at work, then the light is turned off. If it is 8 p.m. or the light is not turned off, therefore the cleaner is at work. You can see right here, we can make an argument. P, it is 8 p.m. Q, the cleaner is at work. R, the light is turned off. Yeah. Okay. In step 1, P implies to Q. It is because in the first sentence, we can see right here, it is 8 p.m. Then the cleaner is at work. You can make it as a P implication to Q. Okay, into the step 2, you can see right here in the second sentence, if the cleaner is not at work, then the light is turned off. If the cleaner is not at work, you use it as a not Q implication to R. Okay, in the step 3, you can see in the third sentence, it is 8 p.m. It is P or the light is turned off. The light is turned off is not R. The light is the light is not turned off, is R. Yeah. Okay. In the fourth step, you can see right here, not R implication by Q. We can make it the second premise to a contrapositive. The second premise into contrapositive. Okay. In step 5, we can make it the premise 1 and premise 4 together to make it as a proof by cases. You can see right here, P or not R implies to Q. P or not R implies to Q. Okay, in sixth step, we can make it as module ponens. You can see right here, if P or not R implies to Q, we can make it as a Q. Okay, that is our last conclusion. Q is the cleaner is at work.